Chapter 4. So now we're going to talk about things that hold atoms together in compounds. And we're going to start with the simple end. The simple end is the ionic bond. And there's an outline. We don't need that. Okay, first of all, what is a chemical bond? I mean, most people, by the time they get to where you are now, you have kind of an idea that if two or more atoms are acting together, there's something holding them together. And in its simplest form, the chemical bond is the attractive force that holds those two atoms together into a more complex unit. And when you consider where that bond originates, think about an atom, right? Rutherford's model. It's got a very dense nucleus with protons and usually neutrons. And you got another one over here. It doesn't have to be the same one for our illustrations. And you got electrons out here, right, all around. When those two atoms approach each other, what do they see first? Electrons. Right? The electrons and or the space that electrons occupy is what interacts to form the bond. Now, two types of bonds. If one atom loses one or more electrons, and I'm going to use an example. Say we start with sodium metal, and we want to react it with chlorine gas. This is a metal. Metals want to lose electrons. Non-metals want to gain electrons. So when they approach one another, the difference in attraction for electrons, we call it electronegativity. The difference in attraction is so much greater for the chlorine that it will steal an electron from that sodium. And actually, since there are two here, we need two there. So two electrons are transferred, and what you end up with is that salt. And this sodium has a positive charge, and that chlorine has a negative charge. So that's an ionic bond, where you form a complete ion. That means electrons have been transferred, removed from one, added to another.
What is beside the name of
Here? Oh, that's an S. Sorry. I try to write my fives more distinctly like that. I used to do them like this, you know, and that gets a little messy. And when I started teaching, I said, you know, I gotta brush up on my handwriting. Okay, so the bond that's holding these together, we call the ionic bond, and it's purely electrostatic. In other words, opposite charges attract each other. And the strength of the bond, we might get into it later, but stream of consciousness. The strength of the bond is due to two things: the magnitude of that charge. So if this were calcium with a 2+ and oxygen with a 2-, the strength of this bond would be greater than that bond because the size of the charge difference. And the other thing is, how close are they together? Because the closer you get two opposite charges together, the stronger they attract. It's kind of like gravity too. The closer you get two bodies, heavenly bodies together, stronger they attract one another. So that's one type of bond. But we can form bonds, or bonds can be formed between two nonmetals. Right. So if we have, let's say, hydrogen gas and oxygen gas. And we give them a little push, like a spark, then they'll form water. Okay? These are both nonmetals. I mean, even though hydrogen's on the left side, it's a nonmetal. Well, we're treating it as a nonmetal, but hydrogen is it's unique. It's in its own universe. But the bond that forms is not ionic. Electrons are not transferred. What you get is a sharing of electrons. And the bond that forms is between that oxygen and two other hydrogens. Right? So we haven't balanced equations yet, have we? Have we? No, good. Okay. That's not balanced, but we will learn how to balance these equations later. So we got two types of bonds. We got the ionic bond. We got the covalent bond. Sharing, complete transfer of electrons. Now there's a little, I'll put this little note at the bottom because every once in a while, most scientists are analysts. In other words, they rip things apart and see what they're made of. Almost anybody can do that. Every now and then, you get a scientist come along who can take those torn apart, put them together into a coherent story. Sometimes we call it a theory. And Linus Pauling was one of those. He took what was known at that time, actually in the late 30s, early 40s. And he wrote a book on the nature of the chemical bond. And it so impressed people that he got a Nobel Prize for it in 1954. But up to that time, people had just been looking at, they were too close. They couldn't see the forest for the trees. So Pauling backed up and said, okay, this is what I think is happening. And he gave a coherent explanation for the chemical bond. All right. I've already talked about this slide. The ionic bond, you have to transfer electrons, and then the forces holding them, the ions together, are purely electrostatic. Right. So what that means is when you get this sodium chloride ions in here, this does not act like a single unit. What you get is what we call a crystal matrix. So you get maybe a sodium ion here, and then surrounding it will be all these anions. And there's one behind and there's one in front. Right? So they had 6 of them surrounding. But each one of these chlorides has a sodium around it. Right? And it forms a 3-dimensional structure. So for ionic compounds, what we are expressing here in this formula is the simplest whole number ratio of the ions. The simplest whole number ratio for calcium oxide would be 1:1, just like sodium chloride. But if we had, maybe instead of oxygen, we had calcium chloride, it would take 2 of those to give you the simplest whole number ratio. And for ionic compounds, we calculate that simplest whole number ratio by balancing the charges. We come out with net zero charge. So 2 pluses and 2 minuses balance each other. But the structure is like that. It's easier to write it this way than we'd have to write it separately for each little tiny cube of salt that you see under the magnifying glass when you spill salt on the table. And we'd have to say something like 10 to the 23rd here and 10 to the 23rd there. That would be ridiculous. So we resort to the simplest whole number ratio, and that solves the problem. Okay.
Is that just for the ionic?
No, just ionic. Yeah, just ionic. The covalents, let's see, we got that coming up. The covalents are often called molecular compounds. Because when you share electrons to form the bonds, you form this unit. And it acts independently of all other water molecules. They do interact with one another, but they're single units. Not like this one. This is not a single unit. It's a simplest whole number ratio of an ionic lattice of cations and anions. But for covalent compounds, these are whole units that act independently. And they're called molecules. Okay. Now, when we characterize the bonds, we're starting off with black and white. Right? It's either this or it's that. The truth of the matter is, when these bonds form, they all have, nearly all have, some ionic and some covalent character. The farther apart the metal is from the nonmetal on the periodic table, the more ionic character they have. As you move closer with metal and nonmetal, then you introduce more covalent character. And it's usually expressed in percentage. Now, when we bond something like this, two nitrogens together, those electrons, when we bond two nitrogens together, then that is purely covalent. And simply because this nitrogen doesn't have a greater purchase on electrons than the other one does. It's a pure sharing. So this one is 100% covalent. And whenever you have like that, this one would be also. Both of the atoms are exactly the same element. Then you get a 100% covalent bond. Otherwise, there is some ionic character in the covalent bonds. And there's some covalent character in the ionic bonds. All right, you're not going to have to do any of those calculations. I'm just stating that as a fact. Okay. What we also have learned is that all the electrons that surround an atom do not participate in the bond. So you got your nucleus here with its protons and neutrons, and then you got your electrons out here. And we can divide them into two types. The valence electrons are in the outermost energy level, so they'll be on this orbit right here. These guys in here are what's called core electrons. These are called valence electrons. The valence electrons are the only ones we have to consider at this point for bonding purposes. Now, I don't think we're going to discuss, let me check before I stick my foot in my mouth. Let's see. Okay. We'll get into that theory next chapter. All right, okay. So we can stick with this model. What I was thinking was that there's another model called the molecular orbital model where every electron goes into the molecule. But for our purposes, we're only going to consider the valence electrons as the ones involved in bonding. And for many applications, this is sufficient. This understanding will get us, 85% of the way to understanding the chemical bond. Okay. For second and third period elements, this rule, the octet rule, is very useful. Okay, so what do I mean by the octet rule? Well, if we, let me see, my mind is slipping. We haven't done, we did electronic configurations, didn't we? No, we did. We did. Okay, good. So in the second and third period, what we've got is, for instance, let's take carbon in the second period. Carbon has six electrons, 6 protons and 6 electrons. And if we write its electronic configuration, we have 1s2, 2s2, and 2p2. These are the principal quantum numbers, and this is the highest energy level. These are the valence electrons, okay, with the highest energy level. They're the ones that are involved in bonding. Now, how would we complete those orbitals? S's have 2 electrons. It's already full. P's can have how many? 6, yeah. So we could put 4 more in here, couldn't we? We have room for 4 electrons. Okay. So how would it get 4 electrons? Well, it would either transfer electrons from a metal or it would share with something else. And if it got those 4 electrons, then what would it look like? It would have 6 here. So that would have 6 here and 2 there. That's 8 electrons. There's your octet. So the octet rule simply states that most elements, at least in the second and third period, most elements tend toward, when they bond with other atoms, they tend toward completing their octet. And when you complete the octet, it looks like the nearest noble gas. So for carbon, this would look like neon. If it were something like, I don't know, sulfur, sulfur would have 16 electrons. If it had 2 electrons added to it, it would look like argon. And it would have a completed octet. It wouldn't be a 2s2p, it'd be a 3s3p. But it'd be a complete octet. This implies stability. When you can completely fill the orbitals, whether it's adding electrons to it from a transfer or sharing electrons. So we're going to anthropomorphize the atom. If we add, say, 4 electrons here, then we say that carbon thinks it has an octet, or sulfur thinks it has an octet, even if it's just sharing the electrons. It doesn't have complete control of the electrons, but it's just as happy. Okay, the ionic bond is formed by transferring of electrons from one atom to another. The valence electron is that in the outermost shell. So for our purposes, you look for the highest principal quantum number, and all the electrons with that principal quantum number are the valence electrons. And the octet rule is operative for the second and third period, and sometimes some of the fourth period elements. The problem, once you get to the fourth period, now you have access to d orbitals, right? Now the octet rule goes out. Okay. So, now that we've been introduced to the octet rule, we're going to use a tool that was created by G.N. Lewis. And we often refer to it as the Lewis dot structure. And what we're doing is with these elements in the first, second, third, and some of the fourth period, we have elements where we can write the symbol for carbon. We would do that. Remember, how many electrons did it have in the outermost shell? 2 plus 2 is 4, right? So we would put those 4 electrons around that symbol. And that would show the valence electrons for that element. Right? So when it came to bond with some other element or atom, like oxygen, for instance, right? Oxygen has 6. 1, 2, 3, 4, 5, and 6. Right? So if carbon shared one of those like that and shared one of these like this, right? Now carbon thinks it has 2, 4, 6. It needs 2 more. So if we put an oxygen on this side, let's see, let's do this, that. Then if this one shared and this one shared, now carbon thinks it has an octet. And oxygen thinks it has an octet. 2, 4, 6, 8. So this Lewis dot structure arrangement helps us work with octets in the bonding environment. Okay, there are some examples. Notice that in the far left column, all those elements have 1 electron in their valence shell, only 1. So for something like sodium, if it's got 1 electron here, and chlorine on the other side, you'll notice has 1, 2, 3, 4, 5, 6, 7. Then rather than share the electrons, sodium just gives up its electron. It goes over here. Right? And now its electron is gone. And if it's deficient in 1 electron, that means it has 1 extra proton or positive charge. Chlorine now has 1 extra electron, gives it a negative charge. But it has an octet here. And sodium now has lost that electron, but its octet is, this electron that was transferred was a 3s electron. But it has a 2s and a 2p orbital underneath it. Right? So once this one's gone, the 2s and 2p become its octet. Right? And it now looks like neon. Okay, that's the result of transfer of electrons to make an octet rather than sharing electrons to make an octet. So we got a slide coming up, and we're going to do valence electrons for each of these examples. Calcium, selenium, and carbon. Calcium, selenium, and carbon. Now we could write out the entire electronic structure and work from there. But since we know how the periodic table is structured, we know that calcium has, it's in the second column, so it has 2 valence electrons, right? The first column has 1 valence electron, second column has 2. So we just put that one and that one. Okay, selenium is, we move over to, from potassium over into the p orbitals. And selenium, look how many electrons selenium would need to look like krypton. It needs 2 electrons to get to krypton, right? It goes 1 to bromine and another 1 to krypton. So in other words, it's 2 electrons deficient. Like that, 6 electrons. And if you count over from the left and skip over the transition metals, right? Potassium, calcium, gallium, germanium, arsenic, selenium. That's 6 steps over. 1, 2, 3, 4, 5, 6. And carbon, we already did carbon. Right, and it's 4. Notice we don't pair them up until we get more than 4. Okay, so 2 valence electrons for calcium, and since calcium is in the 4th period, those 2 electrons are located on the 4s in the 4s subshell. Selenium has a 4s since it's in the same period as calcium, only we move it over, it's got 4s2, but it also has 4p4. So that's 6 valence electrons, and carbon has its 2s and 2p. I thought we were going to draw, oh, I misread it. Determine the number of valence electrons. All right, so I went a step further and drew the Lewis dot structure based upon how many valence electrons it has. Okay, these are just generalizations that can help you with knowing when to use the octet rule and when valence electrons are active. Representative elements. Remember which ones those are? 2 columns on the left, 6 columns on the right. Those are representative elements. Don't ask me where that name came from. Representative what? Well, I guess now they can representative of the octet rule. They have the same number of valence electrons if they're in the same group, right? So the first column, they all have 1 valence electron. Second column, 2. Boron column, 3. Carbon, 4. Nitrogen, pnictogens, 5. Chalcogens, 6. And halogens, 7. And the noble gases have 8. They have complete octet already. That's why they don't play with anybody. They don't form bonds because they don't need to. They've already got their octets. The number of valence electrons for representative elements is the same as the Roman numeral in the old style grouping. So fortunately, this periodic table has both the new and the old style. So if you look at the top of each of the columns, you'll see a Roman numeral 1 on the first column, 1A, then 2A, and then we skip over to boron and it's 3A. Carbon's 4A, nitrogen's 5A, 6A, 7A, and they just put a 0 over the noble gases because they don't want any electrons anyway. Now, when you get down into the transition elements, it gets a little squirrely. That's why their Roman numerals are B's. So we're going to stick to the Roman numeral A's. Those will tell you how many valence electrons are in that column, the Roman numeral. And the maximum number is 8 for the representative elements because we're filling the octet. Okay, now let's write the Lewis symbols for these, O, P, and F. So for oxygen, we look at its column, and it has a 6 Roman numeral. 1, 2, 3, 4, 5, 6. Here we go. And phosphorus, its column is in the pnictogens. It has 5 valence electrons. 1, 2, 3, 4, 5. Okay. And fluorine is a halogen. It's in the Roman numeral 7. 1, 2, 3, 4, 5, 6, 7. Okay. All right. So a valence electron is an electron in the outermost electron shell of an atom. They all valence electrons have the same principal quantum number. The shorthand method developed by scientists to represent the number is called the Lewis symbol or electron dot symbol. I learned it Lewis dot structure. So any one of those is valid to name it. Certain arrangements of valence electrons are more stable than others. That's the valence electron configurations of the noble gases are considered the most stable. So when these atoms interact with one another, if they react, they're trying each one of them to look like a noble gas, either by giving up an electron, accepting an electron, or sharing electrons. They're trending toward noble gas configuration. I just said that, so I'm not going to stop on this slide. The rule that states that atoms lose, gain, or share electrons to form a noble gas is the octet rule. Okay. Now we're talking about ions. We talked about ions a little bit already. But ions have to be subject to neutral atom that loses or gains electrons. And we have special names for them. I've been using those names but haven't defined them. Cations are positive ions. So if we have a simple element with a charge, remember that position is reserved for charge. If we have that, then this is a cation. Now it can have a multiple charge. It can have 2+, 3+, 4+. That's just an example. And the anion then would be the negative. And it also can have multiple negative charges. All right. How does it get those negative charges or positive charges? Gain or loss of electrons. Don't mess with the protons. What happens if you mess with the protons? Well, you're kind of coming in through the back door. You can mess with the protons from the nuclear side, but from chemistry, you don't mess with the protons because when you do, you change the element. Right? The number of protons in the atom defines the element. So carbons always have 6 protons in their nucleus, always. They can have more than one neutron. They can have 6 neutrons, 7 neutrons, 8 neutrons for carbon-14, which is radioactive. But we never change the protons. So the point of that is that if you're going to form an ion, you have to do it by either adding electrons or subtracting electrons. Right? For carbon, let's use something else. Let's use fluorine. Fluorine has a atomic number of 9. That means it has 9 electrons as long as it's neutral. But fluorine is one of those that likes to gain an electron to make its octet. So if it gains an electron, now it has 10 electrons. But it still has 9 protons. So you can look at those as simple negative and positive charges. If this is a negative, 10 negative, and this is a positive with no sign, then you subtract -10 from 9, you get a -1. So it's math. Balance of charges is add and subtract positives and negatives. So if you add an electron, you get a negative charge. If you add 2 electrons, you get 2 negative charges. Think of it as excess. Is it excess negative or excess positive? If it's sodium, it's excess positive. It's more protons than electrons. And that's where the charge on the ion comes from. For individual atoms, I should qualify that, because we do have polyatomic ions that have a charge, but you've got several atoms together, and that's another topic. Okay, and this is just trying to illustrate. On the left, you find sodium, neutral sodium above, and if it loses an electron to a chlorine atom, which is below, now the sodium is excess positive. It lost one of its negatives. And chlorine is excess negative. It gained an electron, a negative. Okay. Give the chemical symbol for each of the following ions. All right. Let's see if we can do this. the ion A, the ion formed when a potassium atom loses one electron. Right? It's going to lose a negative, right? What does that mean? That means now it's excess positive, one positive. So now that becomes like that. The ion formed when the sulfur atom gains two electrons. If it's going to gain two electrons, now it's excess negative. It's excess two negatives. So it's going to be a 2- charge. All right. Atoms can either lose or gain electrons, resulting in the formation of ions, cations, anions. All of those are correct. These are both ions. That's a cation, that's an anion. All right. Let's see. Atoms tend to gain or lose electrons until they have obtained an electron configuration that's the same as that of a noble gas. I can't argue with that. So for this sodium example, it would lose that 3s1 electron. Now it looks like a noble gas, but it doesn't go this way by adding electrons. It goes this way by losing. So if sodium's on this side, it has to wrap around to the next period. Now it looks like neon. All right. So its complete octet was always there, but now that it's lost its 3s valence electron, it has the 2s2p octet. Okay. It's much, much easier and more energy efficient for sodium to lose an electron than it is to gain 7 electrons to make an octet. All right. All right, so now we're restating the obvious. If it's in group 1, Roman numeral 1A, it's always going to be a 1+ charge. Because every element in that group has only one excess electron, and it's going to lose that electron to look like a noble gas. In the second column, it has 2 electrons in its valence shell, and it's still easier to lose 2 than it is to gain 6. So that's why the second group is always a 2+ charge. And then when we get over to aluminum, it's still more efficient to lose 3 electrons than it is to gain 4. Or is it 6? 1, 2, 3, 4, 5. No, gain 5, excuse me. Lose 3 rather than gain 5. So the Roman numeral 3s are going to form 3+ charge. Now boron technically is a nonmetal. It can become charged, right? Because it's right on the border of that line between metals and nonmetals. So any element on that border can act like a metal or a nonmetal, depending on its environment during the reaction. All right, the 7As, always -1 charge. It's efficient for the halogens to gain an electron, and then they just step over 1 and look like a noble gas. Oxygens gain 2 electrons. The chalcogen group and the pnictogen group, they gain 3 electrons. So that's why they are anions, whereas those on the left-hand side, those are cations to look like noble gas configuration. The carbon group can go either way. Right? It can either gain 4 electrons or lose 4 electrons. And it depends on what you're pairing it with. If you pair carbon with a metal, then it's going to gain electrons. If you pair it with a nonmetal, it's not even going to lose electrons, it's going to share electrons. But it can go either way. Now, what do we mean by isoelectronic? Haven't we talked about this yet? Isoelectronic series. When we were doing electron structures, then we talk about isoelectronic series. Maybe we didn't. All that means is that all of these species in the series, this is one example, have exactly the same electronic structure. In this example, there are 1s2, 2s2, and 2p6. Now, of course, that would be neon. They would have the neon configuration. So they left neon out, but you could put neon in there to be part of that series because it already has that configuration. The others, they have to form ions in order to obtain that configuration. All right. So it's just another example. The neon has an atomic number of 10. Magnesium has an atomic number of 12. So neon has 10 protons, magnesium has 12 protons. And in order to get the same number of electrons, magnesium has to undergo a change to an ion. It has to lose 2 electrons to obtain the isoelectronic species that is represented by neon. All right. Choose an alkaline metal, alkaline earth, noble gas, and a halogen so that they have the same, so that they're in the same isoelectronic series. Okay, so the best way to do that is start with a noble gas, right? Which one do we want to start with? Let's say argon. If we start with argon, 18, what would be isoelectronic with argon? It would be chlorine. The halogen would be a -1 charge, right? It has 17 protons, but it has 18 electrons, just like argon. Go the other way, right? We go down to potassium, which has 19 protons, but if we take one of those electrons away, now it has 18 electrons. And if then we go to calcium and take 2 of its electrons away, right, now it has 18 electrons, just like argon. Those are all isoelectronic with neon, as argon. Excuse me. And the electronic configuration for each one of those is the same as argon. 1s2, 2s2, 2p6, 3s2, and 3p6. All right. I already gave you the number of electrons for each one. It's exactly 18 for each one. But the number of protons for each is different. Okay. So we have 19 for potassium. The next one they gave is 20, 18 for argon, and 17 for a halogen. Electronic configuration of magnesium ion. Well, it's going to look like neon. So neon has 2s2 and 2p6. So it should be A. Right. Okay. I think we've hammered this one enough. When you form an ionic compound, you transfer electrons from the metal to the nonmetal. The metal becomes a cation, non-metal becomes an anion, then they attract one another. And if we write the Lewis structure for this example, sodium and chlorine, then we can show the transfer of an electron from sodium and write the cation and anion with their Lewis dot structures intact. Do the same thing for sodium and oxygen. Sodium only needs to lose one electron, but oxygen needs to gain two to fill its octet. So that's why we have two sodiums and one oxygen in that compound. Now that's still a compound. This is an ionic compound. This would be a covalent compound. But they're still compounds because you have two or more different elements in the formula. Right, that's a compound. This would not be a compound. It's only one element. But this one is an ionic compound. This one's a covalent compound. This one is molecular, and that one's not. That one forms the ionic crystal lattice that I was talking about earlier. All right, another example. I don't think we need to. What's the correct definition of the Lewis structure? Well, it's a combination of the element symbol and the number of valence electrons. Now, we've done so far. Actually, we have done some compounds with Lewis structure. We did the sodium and chlorine, but you can do it with. You can draw the Lewis structure for compounds, like for this one. If we had hydrogen here, right, it starts off with one. This one starts off with one, and oxygen starts off with 2,4,6. But in this case, we're going to share these two. We're going to share these two. Remember, and while I'm here, every bond is 2 electrons. So if I draw the structure like this, that's 2 electrons, and that's 2 electrons. Let's see, somebody. I can't see the. Somebody came in. Participants, here we go. Oh, Hannah's back. Okay.
So we've got H2O. Does it matter if you do OH2, or does it have to be H2?
H2O is proper. Yeah. You put the more electronegative. When you're writing covalent compounds, you put the more electronegative to the right and the less electronegative to the left. We haven't named compounds yet, have we? Okay, right. We'll cover that in the rules for naming compounds. When you have ionic compounds, it's easy because you know which one's the cation and which one's the anion. So the cation goes first, anion goes second. When you get to covalent compounds, then you have to look at the periodic table and say, which one's further to the right? That goes in the anion position. And the one that's further to the left goes into the cation position. Yeah, good question.
Yeah.
I mentioned this earlier. Ionic compounds are always written as neutral. So we just balance the charges. Let's see. Positive ions first, I mentioned that. Negative ions second. And then the subscripts tell you how many of each. Okay. So if we were to write, sodium is a metal, phosphorus is a non-metal. So when they form a compound, phosphorus is in that group with nitrogen, and it tends to gain 3 electrons. Right? If you add 3 electrons, you go phosphorus, sulfur, chlorine, argon. 3 steps, you're at noble gas. So it picks up 3 electrons, and sodium can only lose 1. So when it does that, that means you need 3 sodiums to satisfy that 3 electron transfer. So Na3P would be the formula for this compound. And this is an ionic compound. It's a metal and a nonmetal. So how about these? Well, barium, look where barium's from. Barium is toward the bottom of the second column. It's always a 2+. It loses 2 electrons. And we're going to combine it with chlorine, right? So that means we need 2 of these negatives to balance that 2 positives. This one might be a little tricky. If we have iron with this charge and oxygen with a 2- charge, how do you get that to balance, right? An odd and even. The easiest way is to cross multiply. Just take that 2 over here, take that 3 over here. Then you can check yourself, right? 3 times 2 minus is 6 minus, and 2 times 3 plus is 6 plus. So the net is 0. And then we've got lead, 4 plus, and oxygen, 2 minus. All we need is 2 oxygens, and now we've got the balanced charge. Okay, let's see, there's barium chloride, there's iron 3 oxide, and there's lead 4 oxide. How about if we combine aluminum and chlorine? We need 3 of the chlorines to give us 3 negatives to balance that 1 aluminum with the 3 positive. So that's what it would look like. Actually, we're already giving you rules for naming and writing compounds. Just haven't identified them yet. Ionic compounds tend to form solids. They tend to arrange themselves in a regular cation-anion arrangements to balance the charge in what we call a unit cell. So this is what the sodium chloride would look like. And this unit cell, this arrangement, shows you why when you spill salt on a table and look at it with a magnifying glass, you see tiny little cubes. They're cubes because of that arrangement of positives and negatives. The negatives, of course, the chlorines are going to be the green. When you add an electron, it goes, it makes the ion bigger. When you lose an electron, like sodium, it goes, it shrinks it. Now, when we write, I mentioned earlier, when we write the ionic compound, we go for the simplest whole number ratio that will balance charges. And that's often referred to as the formula unit, because it's not molecular. It's not independently moving groups of atoms like the water molecule. So to keep from confusing it with molecular compounds, we call it the formula unit. So NaCl is the formula unit for sodium chloride or table salt. All right. Okay. These elements, we're gonna learn how to name compounds next, but we need to get these firmly in mind. The alkali metals, alkali metals always form a +1 charge. right? There's no other possibility. Alkaline earths always form a 2+ charge. Move over to aluminum, gallium. I thought indium was, yeah. Indium should be there in there too. Indium, gallium, and aluminum always form a 3+ charge. They're fixed. Whenever they form ionic compounds, they're always those fixed charge. And then there are 3 transition metals that always form fixed charges. And there they are. Silver is a +1. Cadmium and zinc are both +2. So those are the fixed metal ion charges. Now, why did I bother to do that? Well, we're going to learn how to name compounds, and we're going to start with binary ionic compounds as our model. Type 1s. Type 1 compounds. These are always formed from metal and non-metal. Always. And the metal is fixed charge. Fixed charge. So that means it has to come from either alkaline metals, alkaline earths, the aluminum group, or zinc, cadmium, or silver. Those are the only choices for this type 1. And because of their fixed charges, we don't have to say in the name what the charge is. We know what it is because of what the element is. So we name the compound, we write the compound as cation first, anion second. For example, that's the cation, that's the anion. Right? We don't write the charges in usually, but that illustrates their position. Then when we name the compound, we just state the element for the cation. You say sodium. Right? And then for the anion, we change the ending to IDE. So this would be sodium chloride. And that satisfies the 2 rules that are part of the naming convention put together by a subcommittee of IUPAC. This is International Union of Pure and Applied Chemists. And there's a subcommittee that does nothing but name compounds. And I know it has several subcommittees of the subcommittee that handle different types of, right? They'll have one that does organic compounds. They have one that does organometallic compounds. They'll have one that does nothing but inorganic compounds. And they devise these rules for us so that when I speak to you as a chemist and I name a compound, you know exactly what I mean. And the first rule is that the name is unambiguous. That is, that name can only be that formula, nothing else. Okay? The second rule is it's non-redundant. We don't want to put something in the name that's already there. So we would not say this. We would not say sodium, Roman numeral 1, chloride. That Roman numeral is there to say that the charge on sodium is +1. We do that for the metals. That's a type 2 rule. Right? But that's redundant. We don't need it. Because of where sodium comes from, we know it's a +1 charge and it's nothing else ever. Okay? Let's take another one. Let's say, how about this one? write this one. Write the formula for this one. Silver. Yeah, let's make it interesting. How about silver bromide? Okay, we need the symbol for silver. Huh? And it's always a +1 charge, isn't it? Bromine, it's a halogen, so it's always a -1 charge. So that's it. We just say AgBr. That's all you need. It's unambiguous and it's not redundant. We could do that with some others. Let's see, maybe we got some examples here we could work with. Yeah, okay.
I think there's examples in the next slide.
Yeah. There you go. So, if we wrote KCl, we just say potassium chloride. If we said magnesium bromide, then we know magnesium comes first and bromine comes second. Magnesium is an alkaline earth. It's always 2+. Bromine is always a -1. That means we need 2 of them. Okay. Calcium oxide, we did that one earlier. Calcium's 2+. It's in the same group as magnesium. 2+, oxide is always 2- because of where it comes from. Why is it 2-? Because it needs 2 more electrons to look like neon. Okay. All right. Type 2 compounds. Similar to type 1, metal and non-metal, but the metal has a variable charge. Okay. Now, once you put it in the compound, it doesn't flip around and have different charges. It's just when it goes into the compound, it assumes one of multiple charges, and it stays with that charge for the compound. Most of those metals come from the transition metal group. All right. We looked at iron before. Iron can either be, iron can be a lot of things, but it's usually either a 2+ or a 3+ charge. So if it's a 3+ charge and we combine it with oxygen, which is a 2-, then 1 and 1 is all we need. But if it's a 3+ and we combine it with oxygen, now we need 2 of these and 3 of those to balance the charges. Okay. Now, how about naming? We name it similarly to this one, but we have to be unambiguous. And the way to be unambiguous with multiple charges is to state the charge in the name. So we say iron, and the charge is a Roman numeral, oxide. Or this one would be iron 3. For the 3+ charge, oxide. Now we give them just enough information so that we can take that name and write this compound. And we're not redundant. We're not saying stuff that doesn't need to be there. Okay, we got some examples here. So copper is one of those that can have a +1 or a +2 charge. So when we combine it with something, we have to say what the charge is. Iron, we did iron already. Instead of oxygen, we could put sulfur in there. Lead. Now lead is technically not in the transition metals. Now see where lead is? It's underneath carbon. But it's a metal, and it has usually one of 2 different charges, either +2 or +4. So we would state lead 4 oxide in this case. How do we know that? We deduce the charge on lead because oxygen is a -2. So with a -4 here, we have to balance the charge with a +4. There. That's why we say lead or oxide. Okay. All right. Now there's a special case I mentioned earlier, these polyatomic ions. Polyatomic ions are just that. They have two or more atoms bound together. And in fact, the binding of these atoms is covalent. It's very strong and they work as an independent group, but they have a charge. So they can enter into these types of arrangements because they have a charge. They could either be on this side or they could be on that side, depending on the charge. Most of them are negatively charged. The only one in there that's not negatively charged is ammonium. So ammonium would take the place of the metal. And since these polyatomic ions have a fixed charge, once you've identified the polyatomic ion, the charge never changes. So if we say ammonium, we mean that. Right, that's unambiguous. So where would it fit in this scenario? It'd be a type 1, right? Because it's a fixed charge. So if we said ammonium chloride, now we would combine it with a chlorine anion, and there would just be 1 and 1. Okay, it would be named like a type 1. You never follow a polyatomic ion with the charge because the charge is known, it's fixed. Now this list, I had to shrink it down to get it all on one page. But the point, what I want to show you here is that the left side and the right side are duplicates of one another. On the left side, we sort by the name of the polyatomic ion. And the right side, we sort by the formula. And I got somebody talking to me. What's going on? Oh, okay. Very good. We'll talk about some more of these polyatomic ions in a minute. Actually, on the next slide. Okay. So, since the rest of them are anions, they could fit in either one of these groups. If you combine it with one of the fixed charge metals, it would be this one, and then the anion would be a polyatomic. But if the metal were variable charge, it would fit in this group. So the first example there, sodium hydroxide. That's a polyatomic there with a -1 charge, +1 charge there. So sodium OH minus is always hydroxide. You don't have to think about adding an ending to it like we did with these. Right? You just state what it is. And then balance the charges. Magnesium nitrate. Nitrate is a polyatomic ion with a -1 charge. Magnesium has a 2+ charge. Right? So we need 2 of those. The polyatomic ions act as a unit. We put the negative charge out here, but it doesn't belong to the oxygen. It belongs to the whole group. So that's why you can't mess with the subscripts. If you do, you change the ion. So we need a parentheses, and we say we need 2 of these for the negative charge that's assigned to each one. 2 negatives balance 2 positives. And then the last one, ammonium sulfate, is similar. This one has two polyatomics together. Ammonium and sulfate is a 2- charge. So we need two of these to balance it. Okay, I know this is a lot to hit you at once. Practice it. There should be lots of practice in the review document for these. All right, that's type 1, type 2, and we've introduced polyatomic ions. Now there's several polyatomic ions. You will have access to this list of polyatomics on an exam. Right? You're not going to have to memorize them. Just be able to find them and recognize them when you see them in a formula. Most of them have oxygen in them. So if you see a metal and then something else out here with 2 or more elements, and one of them is oxygen, it's probably a polyatomic attached to it. So look for it. There's some that don't have oxygen in them, like cyanide. Okay. Or let's see, what's another one? Let's see if I can find one without oxygen. Yeah, there's one that's not azide. Azide. Okay. And let's see, there should be another one. Thiocyanate, that's a good one. Thiocyanate. But the rest of them have oxygen. And what you'll notice is that some of them form groups. The biggest group in there is the ones that's halogens with oxygen. You'll see that you have one in there. I always start with this one. That's chlorate. Polyatomic ion called chlorate. If we take away an oxygen from that, reduce it by 1, it's still got the negative charge. Now this is chloride. And if we take another one away from it, we don't have a suffix that'll accommodate that, so we put a prefix in here and say hypochlorite. Hypo, underneath. Hypodermic, under the skin. And then we'll go the other direction. This is perchlorate. So if you learn this series, then any of the halogens that form polyatomics, you can fit those in here. If you replace this with a bromine, that would be perbromate, bromate, bromide, hypobromite. Or if you substitute iodine in there, you have periodate, iodate, iodite, and hypoiodite. So there you've got 12 polyatomics right there in your head with just a little bit of effort. And there's some others, like sulfate and sulfite. Sulfate's SO4, sulfite's SO3. Nitrate, what we showed you earlier, NO3 minus. Nitrite is NO2 minus. All right. Let's see, and type 3s now. Type 3 compound. So which one have we not attacked yet? We've done metal, non-metal. Now we need non-metal with a non-metal. Okay, these are ionic compounds. These are covalent compounds. But we're going to use the convention that we established for 1s and 2s to name type 3s. Since we don't have ions, then we can't balance charges to write the formula. So instead, we just say how many of each is in the molecule. And we need prefixes for that. We need Greek prefixes here. Mono means one, di is two, tri, tetra, penta, hexa is six, hepta seven, octa, nona, and deca 10. That's as far as we're going. I mean, they go a lot higher than that, but that's all we're going to use. So you just put one in the cation position and one in the anion position, changing its ending to IDE. And you say how many there are. Now, this goes back to your question about which one comes first. Let's use carbon and oxygen. If we combine one carbon and one oxygen, why did I put them in that order? Why didn't I just say OC? Because carbon is to the left of oxygen. It's toward the more metallic side. So it gets the cation position. So we would name this one carbon. And then we would have oxide. You'd have to say how many? Monoxide, carbon monoxide. Everybody's heard about that. Right, that's the one that kills quickly. You know how carbon monoxide works? It suffocates you at the molecular level. It binds with the iron and hemoglobin irreversibly. Well, not irreversibly, but it's difficult to get loose. And that way your cells, your red cells can't transport oxygen to the rest of your body. That's just what it does. Now, one way, if you're still conscious and you haven't been exposed for a long time, they can put you in a hyperbaric chamber with pure oxygen, and it will eventually strip that carbon monoxide off of your red cells and bring you back. But if you go too long, then they may not even be able to bring you back. Okay, notice that we've got one carbon and one oxygen. But if we only have one in the cation position, we don't say mono. Just by convention. We don't say mono here. It starts with di. For this position, it starts with di. For that position, it starts with mono. And notice I didn't say monooxide. I dropped one of the O's. There's a little aesthetics going on here. If we did this one, right, that's the one that's supposed to be the culprit for global warming. This is carbon dioxide. Notice we just say how many there are, because there's no charge to balance. That's on the next slide. There it is. Carbon dioxide. This is unambiguous and not redundant. What's our next example? Sulfur SF6. Well, what if somebody told you that they were doing an experiment with sulfur hexafluoride and you need to put it into a balanced equation? You need to know how to write it. So sulfur, hexa is the prefix for 6. So that's it. That's our compound. Or if they were going to do dinitrogen tetroxide. Dinitrogen tetroxide. That's the formula. Now, if you're presented with choices, and you have to decide how you're going to name the compound. So you look at the formula and say, what kind of naming am I going to use? Type 1, type 2, or type 3? The first thing you do is say, is there a metal present? If there's not a metal, you go straight to type 3. If there's a metal, then you go for a tiebreaker. Where is the metal located? Is it a fixed charge or is it a variable charge? If it's variable, you go to this convention. If it's not, go to this one. If it's a fixed, then you go to the type 1. That's your decision process for naming compounds. right. Now these, I didn't make a big deal of it. The authors call these binary compounds. They're binary because you got a cation, anion, starting with type ones, and then you carry it through. But binary compound usually means two elements only. But since we've introduced polyatomic ions, you have two binding groups. They could both be polyatomics, but they're still, in a sense, binary. Now we want to throw another wrench in the gears and learn how to name acids. When this IUPAC committee had to deal with naming conventions, actually, let me give you an example. Okay. Manganese can be, actually be several times. Most commonly, it's either 2 or 3. If it's a +2, like it is here, we used to call this manganese oxide. That's when I was a student. You just had to know manganese means 2+. So they changed that convention, and now we just say manganese and put the charge in. That's better. But the reason I'm telling you that is they had a more difficult time with acids. This convention that I just mentioned came from, I don't know, early 1700s, 1600s. But the acid naming convention came out of the Dark Ages. Alchemists were naming acids long before this committee was formed. So they had to deal with the naming convention for acids and structure it so that it could be understood and used to name new acids. Okay, so here it goes. The first thing you need for an acid is to start with a hydrogen, at least one hydrogen. It can have 2, 3, I've never seen more than that, hydrogens in the formula. And then you have something else out here. You can have hydrogens over here too, but these hydrogens are the ones responsible for acidity. Right, so if you drink vinegar, right, you know what acid tastes like. It's sour. There's one hydrogen in vinegar, and it dissociates from the molecule and causes the acidity. So first of all, you need that hydrogen. So for example, there you go. Our naming convention at this point is to call this hydrogen chloride. Okay. But if we do that, it has to be a gas. In order to name it as an acid, it has to be dissolved in water. It has to be aqueous. But we base the acid name upon this other convention. So the next thing you do after you've identified it as an acid and put it in water is you look for oxygens. Are there any oxygens in the molecule? In this case, no, there are no oxygens. So if there are no oxygens, you start the name with hydro. And then you take the ending of this one, ides become ix. So it's hydrochloric acid. Okay? You only use hydro when there's no oxygen. Polyatomics can fit in here also. If we had this one, right, we would call that hydrogen cyanide. Okay? But if we put it in water, now there's no oxygen, so we say hydrocyanic acid. Okay? And then the other example they give you there is H2S, hydrosulfuric acid. Now, what if we have oxygen in it? If there's oxygen in the molecule, you drop the hydro. Never say hydro with an oxygen-containing acid. So this first one, HNO3, we would name as hydrogen nitrate, because this is the polyatomic ion nitrate. If we put it in water, now we just take this part of the name and eights become X. Nitric acid. That's it. The other examples they give, H2SO4. SO4 is sulfate, 8 becomes ic, so it's sulfuric. And I mentioned vinegar before, HC2H3O2. Notice there are 3 hydrogens here, but these are covalently bound solid into that polyatomic ion. This is the acidic hydrogen, we call it. So there's oxygen there. We take this one, which is called acetate. That's the acetate polyatomic ion. 8 becomes ic. We say acetic acid. Okay? Now, if you put vinegar on your salad or use vinegar for anything else, what you have is a 5% solution of acetic acid. That's vinegar. All right, here's some other examples. And they're all polyatomic. HNO2. We would normally call that hydrogen, by our previous naming convention, hydrogen nitrite. Right? NO3 is nitrate, NO2 is nitrite. Ites become us, so we say nitrous acid. Right? SO3 is sulfite, sulfurous acid. ClO2, I gave you earlier, was chlorite, so it's chlorous acid. And there's a decision chart if you want to use it. All right, let's see. We're coming down to the wire. 11:30. We go to, oh, good. We got time. Which of the following compounds is named incorrectly? The first one, KNO3. What type of compound is that? Well, it's a metal and a polyatomic with a nonmetal. So it's either a 1 or a 2, right? But potassium is from alkali metals. That makes it a 1. Right, so we would say potassium nitrate. That's the polyatomic ion here. NO3 is nitrate. So that one's named correctly. Okay, how about B? TiO2. TiO2. Right? Where does that one come from? Titanium. It's a transition metal. It has more than one possible charge, so it's a type 2 compound. We just need to determine what's the charge. Because it's a metal, non-metal, it is charged. Right, so -2 for oxygen, that means -4 total, right? So that means this has to be a +4. So we would say titanium 4 oxide. That's wrong. It's not titanium 2, it's titanium 4. Okay, rather than write the rest of them up there, we'll say, all right, where does tin come from? Well, tin's over there just above lead. And it also has multiple possible charge. So it's a type 2 compound, and we have to calculate OH minus is hydroxyl ion, and there are 4 of them, so that's 4 minuses. So tin must be a 4 plus. Tin for hydroxide is correct. How about D? Phosphorus and bromine. Right. They're both nonmetals. That's a type 3 compound. So we just need to say how many of each. Phosphorus, penta, bromide. Penta is 5. And then last one, calcium is a fixed charge, right? It's an alkaline earth. So it's a 2 plus charge, and CrO4 is a 2 minus charge. We just have to say calcium chromate. CrO4 is chromate polyatomic ion, right? It's right there in your list. Right, so the only one that's wrong is B. Was not written correctly. Okay. I mentioned this before. These groups, these polyatomic groups, are covalently bound with a charge. So they hold together as a single unit. And that charge is spread over the entire unit. All right, so if we have hydroxyl, instead of writing the negative there, right, we just write a negative up there. That covers the whole group. I mean, that's just illustration. We always write it this way. You just have to understand that that negative belongs to everybody. I mentioned this earlier. Most polyatomics have a negative charge except for ammonium, and I don't think hydronium is in there. I didn't put hydronium in there. Hydronium is a special case. And when we talk about, let's see, when we get to acids and bases, we'll pick up hydronium again. So don't worry about that one right now. Most ions contain oxygen, except for the ammonium and cyanide, for examples, and the thiocyanate example. The azide, you know about azide. That compound right there, you'll find that in your airbags in your cars. All you have to do is hit it with a little electricity, and it immediately decomposes that nitrate, that azide, into nitrogen gas, just in an instant, and it goes, the bag's right up in your face. So you don't want that unless you're in a crash. Let's see. Yeah, that's nothing new. That's nothing spectacular. 3, number 4, number of pairs of ions exist wherein one member of the pair differs from the other by having a hydrogen atom. Oh, okay. What they're referring to in that number 4 are polyatomic ions like this one. If we start off with this, that polyatomic ion, PO4, 3 minus, needs 3 positives from the hydrogen. And hydrogen in this case assumes a positive charge. So 3 of these balance those 3 minuses. Well, if we take one of those hydrogens away and it leaves its electron behind, then what we have is H2PO4, which was neutral to begin with, but now we've left a negative behind. So that H2PO4 is dihydrogen phosphate. It's a polyatomic ion with a 1 negative charge. We take another hydrogen away. Now we have 1 hydrogen and our phosphate, only now it's a 2 minus charge. So that's monohydrogen phosphate, or monohydrogen. Look it up. Because by our naming convention, I shouldn't have to say monohydrogen phosphate. Where are you? There's phosphate. Here's hydrogen phosphate. Right, okay, yeah. We don't say monohydrogen. Stick with the convention. That's just hydrogen phosphate. This is dihydrogen phosphate. And if we lose that other hydrogen, that gives us simply phosphate. That's another way to expand your memory on polyatomics. If you just remove a hydrogen, the hydrogen leaves an electron behind, so the charge bumps up, bumps to a negative. Take 2 away, bumps up 2 negatives or 3 negatives. All right, there's polyatomics. Let's see, term in the same way. Positive and negative charges present must add to 0. That's nothing new. We already did this one. I think that's a duplicate slide. Yeah, I don't know how that got in there. All right, so let's try another example. What's the correct chemical formula for the combination of ammonium with its positive charge and carbonate, CO3 2 minus? They're both polyatomics, so we need 2 positives to balance that 1 with 2 negative, correct? And everybody knows carbonates. If you drink pop, carbonated beverages, it's not made from this. In fact, carbonated beverages are, we put CO2 gas and we bubble it through water. Right? And that gives us there's an oxygen. This is carbonate, right? Carbonate. It's got an oxygen. We don't say hydro. This is an acid. So 8 becomes it. This is carbonic acid. So you're drinking acid with pop. Actually, that's not the only acid in pop. Usually they put a little phosphoric acid in there too. That's why if you ever seen this done? You take a can of Coke, you pop it open and you take a nail, drop the nail in there. Not galvanized, straight nail. And come back in a week and it's gone. It's converted to iron 3 phosphate. Iron 3, I think. It's the phosphoric acid that does the damage, not the carbonic acid. But later on, we'll talk about acids and bases. This is a weak acid, phosphoric acid is a weak acid. They have a buffering effect. So if you have an upset stomach, Actually, you used to be able to buy Coke syrup years and years ago. And my wife told me, we never did it in my household, but her mother had some Coke syrup. And if your kid had an upset stomach, you give them a spoonful of Coke syrup and it just settled their stomach right down. Now I think they sell it as, what's that upset stomach stuff? It's sugary. Remember the name of it? Shoot, I can't remember the name. But all it is two different types of sugar. And you just take a spoonful of that, it settles your stomach right down. But this does it by buffering Coke syrup. Coke syrup does two things. Actually, it's got lots of sugar in it. Right? Everybody knows that. But it's got that weak acid buffering effect. We'll talk about that more later. Okay. All right. This last slide. I think it's the last slide. Oh, yeah. Okay. So this is the last slide. Waters of hydration. When we name a compound that has water attached to it, there's another convention. You take the front part of the name, which is always ionic, and then you add the water on the end of it. So where did that come from? Well, if you say you form a compound in aqueous solution, you've created a chemical reaction and you form the compound and you want to recover it. So if it forms a solid, you let it settle and filter it out. If it's soluble, then you evaporate the water and leave the solid behind. And if you dry it at 105 degrees Celsius, which is just above the boiling point of water, you'll get rid of most of the water. But what we've discovered is if you put it back in the oven and dry it at 150 degrees Celsius, you lose more water. So what's happened is there's some water in that crystal structure. And it's usually a fixed molar ratio. So our example here is this compound. Let's see. Zinc has a fixed charge, right? So it's a type 1 compound. So we just say zinc sulfate. All right. But zinc sulfate has a tendency to accumulate when we dry it at 105 degrees, it'll hang on to 7 water molecules in its crystal structure. So for every 1 mole of that compound, you have 7 moles of that water. Or for every 1 molecule of zinc sulfate, formula unit. For 1 formula unit of zinc sulfate, you have 7 molecules of water attached to it. And that's the way we write it. We put that dot in the middle of the line. These are waters of hydration. And then we add them to the name as hepta for 7, hydrate. Okay? That's all you have to do. Just add them with the prefix to say how many there are. I had my 2-semester chemistry class do a waters of hydration experiment, and we used copper sulfate. Actually, copper 2 sulfate with 5 waters. So this would be copper 2 sulfate, and it would be penta hydrate. Okay. All right. So that's all the naming conventions I've got for you now. Let's see. Do we want to tackle these things, concept questions? After placing a soft, lustrous, and malleable material in a container of yellowish gas A violent reaction occurs, leaving white crystalline material. You decide to break the rule, never taste chemicals in a laboratory, and find that it tastes very salty. What you have there is a soft, lustrous, malleable material, that's a metal. And then a yellowish gas is a non-metal. So we've got a reaction that produces an ionic solid, and it tastes salty. So let's see. B would be two materials are likely to be elements sodium and chlorine reacting to share all right, there's the key. They could be sodium, metal, and chlorine gas, but they don't share electrons. They transfer electrons. That's why C is a better answer. Transfer electrons to produce an ionic compound, sodium chloride. So that's why C is probably the best answer for that one. Fill in the following table with the correct information. It looks like it's already filled in. Oh, no, 1 and 2 are represented in the answers. Okay. The first one, NaHCO3, we want to name that compound. Okay. So type 1, type 2, type 3. Type 1. Sodium is a fixed charge. This is a polyatomic. Notice it's got an oxygen here and got several elements. This is hydrogen carbonate. So we just say sodium, hydrogen carbonate. Now you can buy this on the grocer's shelf. Only they don't call it hydrogen carbonate. They call it, I'm sorry? Yeah, baking soda, sodium bicarbonate. But they use the old form. Let's see. And 2 is MgHCO3. MgHCO3 twice. This is just magnesium hydrogen carbonate. 3, we're going to take sodium phosphate and write the name. So we have sodium and phosphate, which is a 3- charge. This is 1+, so we need, need a parentheses for sodium. Just need a 3, because there's only one atom there. All right, and then 4 is magnesium phosphate. We have magnesium phosphate. This is 3-, this is 2+. Remember how we deal with those? Cross multiply. So we bring a 3 over here, and we put a 2 over here outside the parentheses. Okay. So the one that's got all those right answers is there. Oh, is that it? That's it.